Hello, George Romanic here. Today we will talk about Brownian motion of COVID-19 particles. As we all know, COVID-19 is a virus that is currently a global pandemic. And this virus is spread through droplets of saliva that come out from our mouth or nose when we talk, smile, sneeze, and so on. At the end of this video, you will learn how the random motion of molecules in the air influences the propagation of this virus in a room that is in perfect thermal equilibrium. So the only motion is the Brownian motion. You will also learn what exactly Brownian motion is, and of course you will get some knowledge on kinetic theory of gases and movement of microscopic particles in our atmosphere. So without any further ado, let's go and mathematically derive this concept of Brownian motion of COVID-19. Our COVID-19 particle has a spherical shape with these protuberances sticking outside, and this is clearly sketched, that is not to scale. The diameter of the particle is 600 to 140 nanometers, and nanometer is 10 to the power of -9 meters, which is billion times smaller than a meter. However, as I said in the introduction, the virus is not transmitted in this pure form, but it is rather immersed in a droplet of saliva. So the droplet is like that, and then there is virus inside. And the diameter of this droplet is between 1 and 500 micrometers. And this, I said, 60 to 140 nanometers. Micrometer is 10 to the power of -6 meters, which is million times smaller than a meter. Now, what happens is that this droplet, let's say this is our droplet with the virus inside, is in the air surrounded by millions and millions and millions of molecules and atoms. And they are bombarding this droplet from all sides. We talked in my video on atmosphere as a continuum that we can have small scale fluctuations in, for example, density of air molecules, and it can happen that in a given moment in time there are a lot of molecules perhaps moving in this direction, and they hit the particle from kind of below, as I plotted it here. So the particle will move upward. However, after a short period of time, perhaps there are more molecules on this side of the particle hitting it to the right than there are here hitting it to the left, because of these small scale fluctuations. So particle goes right. And you can extend this clearly to further times, and you will see that the motion of this virus is random. And this random motion is called Brownian motion, after Robert Brown, who discovered it in 1827 and published in a large manuscript. Now, from kinetic theory of gases, we can already estimate the kinetic energy that is available in these molecules, as well as this microscopic droplet. Now, we know that mean kinetic energy in one direction, let's say x direction, is equal 1 over 2 k times T, where k is Boltzmann constant and T is temperature in kelvins. And this is the basic equation in kinetic theory of gases. Now, we also know that mean kinetic energy, again, let's say in the x direction, is 1 over 2 mass times the mean times the square of mean velocity in that direction, in this case x direction. So if I just combine these two equations, I can already see that mass times velocity squared, but mean, is equal to kt. And this is equation that we will use later in our derivation. For now, you can just remember that these two equations estimate the mean kinetic energy available in these microscopic particles. That doesn't mean that any of these particles has exactly this value of kinetic energy, but some of them have more, some of them have less, but on average this is the kinetic energy available in molecules as well as these microscopic droplets. Okay. Now let's construct a model that can represent this random motion of droplet that contains COVID-19. Well, to do that I will use second Newton's law that says that mass times acceleration, for example in x direction, is the sum of all forces in the x direction. Now, I need to see what are the forces that are affecting the motion of this droplet. Well, mass times acceleration is equal, and as you can see, I'm constructing model in the x direction, and then similar to my previous video on the random walk, you will see how easy it is to generalize it to three directions. Well, what are the forces acting on this droplet? Well, obvious force is the random bombardment of these molecules that are surrounding it, and I will call that Fr, random force. However, as the droplet is moving through the air, it is also experiencing viscous forces that we talked about in a series of my previous videos. So I suggest you check these. And these viscous forces try to slow down the movement of this droplet. Well, we know that the viscous force exerted on a spherical object, and this droplet is a spherical object, can be expressed using Stokes' law, that is 6 pi mu r Vx, where mu is dynamic coefficient of viscosity, r is the radius of this droplet, and Vx is the velocity of the droplet that it gains due to this Brownian motion. Now pi, if you don't know what the pi is, then you might as well close this video and go and watch some beauty blogger videos. Okay, this equation cannot be derived from some underlying physical principle. It comes from experimentation and dimensional analysis, so if you don't know this formula, you will just have to believe me. Now I will substitute this form of Fv into my second Newton's law, and I will get that mass, acceleration, I will rewrite it as second derivative of the position, is and I will actually move Fv to the left side, so it will become plus, and then I have 6 pi mu r Vx equals Fr. And this equation actually has its name. It is called Langevin equation. It can be solved explicitly for x, because I can rewrite Vx as dx over dt. But instead of solving this equation, we will do something much more clever that I saw in the book of Richard Feynman. We will analyze term by term, and we will conclude what the solution needs to be by analyzing these terms. To do that, I will first multiply this equation by x. And I will clearly get that mx d second x dt squared, there should be squared here, plus 6 pi mu r x Vx, I will now rewrite as dx over dt, is equal x Fr. Now I will also average this equation. Now what do I mean by average? Well, I mean similar what I did in my previous video. I can either let this particle move for a very long time and then average that movement over a very long time, so not 5 steps or 10 steps, but million steps, or I can release many particles and then do ensemble average of these many particles and how they move, either of these, and I represent that with this sign. So when I average this equation, then I basically just add here this averaging sign. I don't have to average these constants, of course. And you can see that I have these three terms. So this would be my term 1, term 2, and term 3. What I will do now, I will analyze these three terms to see what they tell me. So let's do that. Term number 1. I can rewrite this term as, I will just say term number 1. I can rewrite it in the following format. I can say that this expression here is equal m d mean of x dx dt over dt and minus m mean of dx over dt everything squared. You can clearly convince yourself that these two terms are exactly the same as this term, because when you do differentiation of this using chain rule, you will get cancellation with this term, and the only term that will survive will look exactly like that. So this is exactly the same. However, the benefit of expanding term 1 in this format is that this term is actually 0. And this term is 0 because distance times velocity has a mean that doesn't depend on time. If that mean depends on time, that after some period of time the motion of this particle would either slow down or speed up, but I'm saying it will always be the same, because the kinetic energy of molecules that are bombarding COVID-19 droplet doesn't change with time. So the temperature of the room, for example, is constant, so this term has to collapse to 0. So term 1 can be expressed in this form. Now, term number 2, that involves Stokes force, I can rewrite it as 6 pi mu, and then I will move this x under the differentiation, and I will get d of x squared, but mean, so mean square displacement over dt, but I have to put here 1/2, because when I move x here, it gets this half, so I have to put, it gets squared, so I have to put half here, which means this is simply equal to 3 pi mu r d mean x squared over dt. And finally, term number 3, well, this is very simple. That term has to be 0, because this force, I'm talking throughout this video that this force is random, so average over time has to be 0. Random means the motion of this droplet is equally likely in any direction, so over a long period of time the average has to be 0. Now, when I combine these three, I will get the following. So, combining 1, 2, and 3 that I expanded previously gives me that minus m mean of dx over dt squared plus 3 pi mu r d mean of x squared over dt equals 0. However, this is velocity. So minus m, so this is velocity in the x direction, mean value of that velocity, but squared, is equal 3 pi minus, so I will move this to the right side, minus 3 pi mu r d x squared over dt. But now we go back. This term can be represented using this equation here. M Vx squared mean is kt. So I will use that fact and I will substitute here kt is equal to, so minus and minus gives plus, 3 pi mu r dx square over dt. And now this is differential equation that separates variables. Everybody should know how to solve that. So my solution will be that mean square displacement is equal to kt over 3 pi mu r times t. And voila! This is exactly the same expression that we obtained in my previous, so this is time, not z, this is time, that we obtained in my previous video on random walk. And I hope now that you realize how beautiful mathematics and physics are. Because using pure physical argument, second Newton's law namely, we get expression that we obtained in the previous video using purely mathematical argument. This was alpha in the previous video, if you remember. And this is expression for if I consider one-dimensional case. Similar to previous video, I can extend this to 3 dimensions, where r is distance in 3 dimensions, and then mean square displacement in 3 dimensions. I just multiply this with 3, which means that just these 3 will disappear. I get it is kt over pi mu r times t. And this is the 3-dimensional extension of this expression, which means that this equation here tells me what is the average distance, mean square displacement of this particle that starts here and moves through air due to Brownian motion. Okay, now let's plug in some numbers and see how far this particle will actually move due to Brownian motion. So I will here at the end have a small table. Here I will have r, because I can specify r and then solve this equation for t, of course. And distances will be 1 micrometer, 1 millimeter, and 2 meters. And then I will calculate time that particle of COVID-19 will move over that distance. So the question is, after what period of time COVID-19 particle will move over a distance that is 1 micron, 1 micrometer? Well, if you solve this equation for t and you plug in numbers, and here I use that t is room temperature 293 kelvins, and these other are constants that I will not write down here to save time. Then time it takes for COVID-19 to traverse 1 micrometer is 1.8 milliseconds, thousandth of a second. How much time it takes for COVID-19 particle to move over a distance of 1 millimeter? Well, around 1.9 hours. How much time it takes for COVID-19 particle to move over a distance of 2 meters? Well, around 899 years. Okay, now you might say, well, this doesn't make much sense. I expected that the spread of COVID-19 will be much faster. After all, we see in the news and all over the media that this is highly transmittable virus. So how is it possible that it takes so much time to go over a distance of just 2 meters? Well, please try to remember that the derivation that we did here is idealized in a sense that the virus is propagating only and exclusively only due to Brownian motion and nothing else. So there are no external forces influencing the propagation of this virus. Now, this is this is never true in real conditions. For example, when you are in the room, there is a lot of drift, wind. Your presence in the room introduces some thermal convection, and all these drifts are so significant to a small particle such as a droplet of saliva that contains COVID-19 that it would be like a hurricane for us standing outside, because the size of these particles is very, very small. As we saw, it is between 100 and 500 micrometers. So we could improve the analysis by considering the following extension of our model. Well, we saw that our original model that we used to represent the motion of our particle is m d second x dt squared equals fr minus fv. In other words, the position of the particle only depended on the random force due to bombardment of the molecules and viscous force. However, we can add here external force. And this external force can result in a predominant direction of the propagation of COVID-19. Namely, when we exhale, then, for example, if this is our mouth, when we exhale, then if we push air in that direction, and this is the COVID-19 particle, then it will still exhibit random Brownian motion, but as you can see, it will be biased towards this direction because we just exhaled in that direction. And this predominant direction can be modeled using some form of external force. Now, if you would like me to cover this model in one of the future videos where we will have some drift velocity that will significantly influence the propagation of COVID-19, let me know in the comment section below and I will prepare a video on that subject. In the meantime, I hope you enjoyed this video. Have an excellent rest of the day and see you in the next video. Cheers!